Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 38, we will talk about k-nearest neighbors algorithm, and the concepts that we will cover will be on the algorithm itself, and then we will talk about the different ways we can use this algorithm. We will learn about the distance matrix, the value of k. We will also talk about the cards of dimensionality, and finally we will demonstrate this particular algorithm using Python. So KNN is a non-parametric instance-based supervised algorithm, and this predicts an outcome using the k most similar training samples. That is, it predicts the output of a new observation by aggregating the outputs of its k closest training instances based on a distance measure. So for example, there is a group of points and I want to predict for a new point where it would be basically looking into the nearest points which are there, and based on what kind of, what class those points belongs to, we will actually predict the class of the new point. So it's the learning is actually deferred in this particular case. So it is known as lazy learning until prediction time. That is, decisions are made by comparing a new instance with stored training examples. Objects that are close in feature space tend to behave similarly. So that's the main principle behind using KNN. And similar locations or similar kind of households or similar kind of trips or similar kind of land parcels are expected to behave similarly, and that is the principle that is used to predict the outcome of a particular location or a household or so on. So in that way, that means because it is near to some other things, it is expected to behave in the same way. So the different steps that usually we follow: first we choose the value of k, that is how many number of neighbors we should compare this with. That means how many numbers of neighbors around this particular instance which we are trying to predict for, we will consider. Then compute distance from query point to all the training points. So what is the distance from this new point to all the other points, surrounding points which are training point, and how do I compute that distance? That's another important thing. Then select the k nearest point. Once we have selected that, then we aggregate the outputs. Depending on either we are going for regression or classification, the aggregation method is different, but we take that and then accordingly we can predict for the new point. So for classification, what we do is the output is categorical and selection is through majority vote among the k neighbors. So if most of the neighbors belong to a particular class, whichever is the more dominant class, that would be the class predicted for the new instance. And for example, 3 neighbors say residential and 2 say commercial, then the prediction for the new class is going to be residential. Similarly, in case of regression, what we do is it's a little bit different. Instead of taking a voting for the actual class, here output is of course continuous because it's a regression model, and what we do is the prediction is the average or the weighted average of the neighbors. So whatever value the neighbors have got, the continuous value, and we will take a weighted average or an average of that particular value, and then we will predict the value for the new instance. And KNN is commonly used as a baseline or benchmark model. So it's a very simple model. It could be fitted to nonlinear data and all. So it could be easily computed. So in that way, that's why usually we use KNN as the baseline or the benchmark model, and against this we will compare all the other models to see which one is performing better, and maybe we will choose that particular model. So the k nearest neighbor algorithm, the most simplified form of it is where the value is, we only consider one nearest neighbor, that is 1 in n. And what we do is, what we can do, suppose we have got this point, as you can see in this particular image over here. So this is one point we are now taking, and you can see for each point I have divided the space using Voronoi diagram or Voronoi tessellations to divide this particular zone around that point, right? So as you know, in Voronoi diagrams, what we do is we connect all the points and then take perpendicular bisectors of this point, and wherever the perpendicular, like for example, if I connect these 2 points, this is the perpendicular bisector. Now, if I connect these 2 points, this is the perpendicular bisector. If I connect this point, this would be the perpendicular bisector. So, in this way, whatever that space comes out, that is the the Voronoi diagram, you can say. So, this Voronoi tessellation, you can say. So, that means any point which falls on, suppose this new point is x, it falls over in this particular zone. So, any point which falls anywhere in this zone would be same as whatever is this particular point. So, that is the idea of the k nearest neighbors, and in this case only one value is 1, we have taken the value of k as 1. So, assigns label of the closest trailing point, whichever is closest to this particular new point, x is the new point. So, whatever value is within this Voronoi diagram is basically the closest point, and it is very sensitive to noise, of course, that is also understood. So, all possible points within a sample's Voronoi cell have the same have the sample as the nearest neighbor. So, that is the principle, accordingly we can say. Now, the problem is this also can change depending on the distance matrix, and the entire decision surface can also be changed based on that. That is, how do I measure distance? So, in this case we have used a Voronoi tessellation, but suppose this x value is a new value comes over here. It is, and in the, suppose I take 3k, these are the 3 neighbors, k value equal to 3 that we are considering. Now, this is a distance between them. So, how exactly we are measuring the distance, that also governs the outcome. So, in this case distance could be measured in different ways. It could be straight away Euclidean distance, which is nothing but the straight line distance in the feature space, and this is used when features are more or less continuous. But sometimes we need to do scaling, as we have done earlier. That means we can do normalization, and we can scale it using either the z score value, or it could be based on minimum maximum difference and so on. Then it could be based on Manhattan distance, or otherwise known as city block distance. It is a grid based movement pattern. So, that means I do not go directly, I will go following a particular grid that is there. So, it's a measured distance. The distance is measured along axes, and it is basically more robust to outliers considered to Euclidean measures, and you can see the formula for that over here, and this is the formula for a linear distance measure, right. So, in this way we can use many other distance form. So, one of the distance form which is commonly used even in the machine learning algorithms is the Minkowski distance. Which one? This is a general form of both Euclidean and Manhattan. That means, by changing some part of this particular equation, that is the value of p, I can either it would become a Euclidean, or if Manhattan value p equal to 1, it would take the form of the Manhattan distance, right. So, it is a general form. So, it is a very popular one. So, we can mimic any one of them by changing the value of p. And this p value actually controls the neighborhood geometry, and it also controls how strongly a large difference in one features affects the overall distance between 2 points. And so, what it means is suppose there are multiple features for each point. Features means all the attributes of that particular point, and in that case one of few features are larger considered to other, and then actually this can be this formula or the way we use p, that can actually govern how we should consider that, and this is useful for tuning sensitivity to large differences. Now, you can see over here, if p equal to 1, it is Manhattan distance. So, the neighborhood shape will be in 2D form, of course, but we can also have 3D shapes as well. So, this would be in diamond form, and it's like a grid like movement. Euclidean takes a circle form, so it's a straight line distance. Minkowski takes a square circle, which penalizes large differences more, and then there is p when it tends to infinity, it takes Chevy-Chev's forms, which is a square, and then accordingly we can also take cosine distance, which is also measures the orientation, in which direction it is, not only the magnitude, and it also ignores the absolute size differences, and sometimes this is important for behavioral or proportion based data. So, in this case we will use this formula, and then there could be the Mahalanobis distance, or the Hamming distance. Now Moholy-Nevis distance is used when features are correlated. So what happens is we have to choose what kind of distance depending on that particular set of data or what we are dealing with. Accordingly we can choose the distance. Then comes the value of k. How do I choose the value of k, right? One is how take the distance of p, and then the distance of between the points, and then how do I choose the number of points. So if the value is very small, that is we take a k value as 1 to 3, obviously there is low bias, but there could be high variance. So the model could fit to local pattern and noise, and it may lead to overfitting. Now looking at the image, if you see that in the first case where k equal to 4, that is we are considering only 4 nearest neighbors, in that and we say that there are two classes. One is of course the blue rectangles, which is class A, and then there are the saffron triangles, which is class B. Now the point that we are trying to classify is of course the point given in green. Now when we take k equal to 4 and we take distance as Euclidean, which will form a circle, you see that in the first instance that the classification of this new point would be class A, which is nothing but that which would be same as the the four objects that falls within that circle. So which is nothing but the blue rectangles, blue squares. Now in the next image, what we are doing is we are just simply changing the value of k to 11. So in this case, that means we are going for a large k value in this case. So we see that there are around 5 blue rectangles, and then there are 6 saffron triangles. So in that case, of course, the classification would be class B. So that is one thing we need to understand. That means the k value determines quite a lot. Like if the k value is very high, then the bias then for large k the bias would be high, but it would have low variance. But the model averages over many points, smoothing noise, but underfitting could be a problem of underfitting. That means it is not that properly explaining that particular model. So we need to find the optimal value of k as per data. Usually this is chosen as an odd number, and we sometimes follow certain strategy, like we can do cross validation. That means we can change the values of k and see how it is performing. Or there could be a rule of thumb where k is almost like root of n, where n is the number of training points that we are using. So based on that, we can determine that what should be the right value of k as well. So along with that, we have certain other issues that we have to be careful about. This KNN model, the prediction accuracy often degrades as the number of attributes increase, since sometimes a lot of irrelevant features. What we have seen earlier is when we do a linear regression, logistic regression, that not all variables are selected, only the ones which are contributing more or which are significant, those are selected. So in this case, because we are increasing the value of k, sometimes we are increasing the number of features that are there. Sometimes irrelevant features get selected in the selection process, and it can overwhelm the influence of the relevant features, making distance-based similarity measures less reliable, right? So there could be several remedies to it, of course. And we can remove the irrelevant attributes during pre-processing, and we can apply feature weighting to emphasize the important variables, and we can increase k little by little to reduce noise without over smoothing. Now one of the ways to introduce feature weight is by saying that not all neighbors so we can do some amount of feature weighing, and along with that we can follow certain other things as well to improve the performance of KNN models. Like we can take distance weight KNN, we can take the closer point should be more important or having more influence considered to the the points which are far away. So we can use this kind of weights, and this can reduce the impact of distance noisy points. Or we can do feature scaling as well. For example, we can use this like z-score standardization or minimum max scaling to standardize the distances. Like distance based algorithms are scale sensitive, as features with larger numeric ranges disproportionately influence the distance. So of course scaling comes handy in this particular case. And so we will use KNN when small to medium sized data sets are utilized, low to moderate dimensionality data sets are there, and when local similarity also makes sense, like not everything is can be determined like that, and then noise and outliers are relatively less compared to in some other cases. So that is when we can use KNN, and it's a very simple model, and it could be again I will say that this is a baseline model, and we usually compare the performances of other models with this to say that how well those models are performing. So this is the data set that we have used in this particular Python example. We have used this data set earlier during our decision trees, and so we have seen that we are trying to decide should I drive bicycle or not today. So there are several yeses and several nos, and these are the features, that is day there are 14 days, and the features are weather, temperature, humidity and wind. So that means with these features varying, should I take a decision to drive bicycle or not. So here you can see the Python program. So this we will first import pandas as PD, and then we will import sklearn. We are importing different aspects or different modules from sklearn, and you can select like model selection, import, train, test, split, grid search, CV, and then we are importing the one-hot encoder, the column transformers, pipeline, the K neighbors classifier, and then of course these are the matrices that we are going to incorporate as well: accuracy score, confusion matrix, classification report, and ROC AUC score. First we load the file, that is CSV file. So drive underscore bicycle underscore 3x, that's the name of the file, and we are putting that in a data frame, and then once we have done that, then we are trying to understand what are the feature columns. So we are first storing weather, temperature, humidity, wind in feature this particular variable, and then the target column is also being stored, which is drive bicycle, and then we can copy them in X and Y. Of course X and Y are this particular variables that we are going to use. Like we can what the Y value could be also mapped into ones and zeros instead of yes or no. So that is what we have done over here. So we are mapping both the target, we are taking both the target as well as the feature and storing them in X and Y. And then we are doing pre-processing, because most of the the features that we are using are all categorical. So we are using the one-hot encoder through transformers, and this will encode that particular feature columns, and for things which are not there, it can ignore those, and the remaining ones, if there are some more columns, those could be dropped. Then we are training and we are splitting the data for train and test as we have done earlier. So 0.30 is taken as the test size, so that means 30% will be reserved for testing. Random state remains as 42, and stratify equal to y. It keeps the class balance similar in the train and test sets. So then we put the pipeline in place. That is, we first put pre-process, then we will call the model. So this is the pipeline that we are building, and then something new comes in. That is, we are introducing this param grid, which is like the hyperparameter, how I tune the hyperparameters in the cross validation stage. And so what we are doing is the number of neighbors would be changing from 1 to 3 to 5, 7, and we would be testing with each one of them what would be the result. And then we will use weights, that is this uniform weight versus distant weighted voting. Both we will introduce. We will see which one will work better in this particular data set. And over here we are using Minkowski's, where p equal to 2, that means it is Euclidean distance. Now grid search CV is then what is being called. what it does is it systematically tests different hyperparameter combinations. So it is a way for tuning the hyperparameters, right? So we have introduced the hyperparameters over here. Now it uses different combinations of that, and along with that it will also do cross validation to select the best performing model. Now what it does is this grid.fit actually when we are trying to, we are trying to fit every combination that is there in this param grid, and then what happens is, if we are, because we are using CV equal to 5, we are doing the combination with we are doing 5-fold cross validation. That means we are dividing the data into 5 groups, and then for we are training it using 4 groups and testing it with 1 group, and accordingly once we have done that, we are finding the average values of the the best fit solution. And so the then grid.fit, once it is trained, the best model grid.best underscore estimator underscore stores the best model that is generated after your cross validation, and in underscore jobs equal to -1 actually says that okay, how much of CPU would be utilized, and so on. So once I have developed the model, I can predict the model. So we are predicting for X test. So this is the test data for which we are doing prediction, and then we are predicting we are calculating the accuracy score based on Y test and Y pred, that is the actual value and the predicted value of those variables. And then we are using we are also preparing the confusion matrix, and then we are doing the classification report, which we are now storing in report text, and then we are also predicting the probability as well. So once it is done, we are creating once after the predicting probability, we can run the ROC AUC score, and we are storing that value. And once this results once these are all out, we are storing all this in this particular list results, and we are storing in this dictionary, in this results, like for each one of this we are storing the actual values, and then we are able to print this all the values that we have just done over here. And we are like print CV based accuracy results, we can print the CV based accuracy part. Then for test accuracy, confusion matrix, we are printing one by one. So over here you can see that the model metric, the final metric that is being chosen, that is also being reported. And so this is this grid best parameters that is being chosen after iteration. You're finding the best possible parameters for this model. So model metric is Minkowski model, Neighbours is taken as 15, model is and then model best is distance, CV value came as around 0.96, test accuracy is 1, confusion matrix is perfectly predicted, and then we have the classification report, which is, because the data set is very small, it is coming like that, but and then ROC AUC value is perfect one. So actually it seems like overfitting because all the values are very perfect, but because the data set is very small. So these are some of the references that we have used. And to conclude, K nearest neighbors leverages local similarity in feature space to make flexible non-parametric predictions, making it an effective baseline model when distance metrics, feature scaling and the choice of K are carefully handled. Thank you.